If you've been tracking AI research lately, you've probably noticed a quiet but massive shift happening under the hood. Transformers have ruled sequence modeling for years, but they're hitting real computational walls. And that's exactly why state space models, particularly the Mamba architecture, are suddenly dominating conferences and breaking benchmarks. Let's break down why they work, how they actually process information, and what this means for the future of large-scale AI. At its core, a transformer relies on self-attention. That means every token in a sequence looks at every other token to compute relationships. It's powerful, but it scales quadratically with sequence length. Double the context, and you don't just double the compute, you quadruple it. For long documents, video, or high-resolution audio, that becomes a hard ceiling. State space models flip that equation. They treat sequence modeling as a continuous-time dynamical system, borrowing directly from control theory and signal processing. Instead of attending to the whole sequence at once, they compress the input into a hidden state and evolve it forward step by step. The key insight is that this evolution can be computed in linear time, and more importantly, it can be parallelized during training while remaining strictly sequential during inference. Let's get into the mechanics. The original Mamba architecture uses a structured state space layer called S4, but it's parameterized in a way that makes it hardware-aware. The continuous system is discretized using the zero-order hold method, which converts the differential equation into a discrete recurrence relation. What makes Mamba different from earlier SSMs is the data-dependent gating. Instead of fixed parameters, the transition matrix, input projection, and output projection are all dynamically computed from the input sequence itself. This turns the model into a selective scan mechanism. It decides at each step how much information to retain, how much to forget, and how much to pass forward. That's why it handles long-range dependencies so efficiently without drowning in attention weights. Training dynamics are where things get interesting. Because the state update is linear in the hidden dimension, you can unroll the recurrence and compute gradients efficiently using truncated backpropagation through time. But Mamba avoids the vanishing gradient problem by using a carefully designed discretization step size that adapts to the input. During training, you parallelize the scan using associative scan algorithms, which lets you compute the entire sequence state in logarithmic time on modern GPUs. Then at inference, you drop the parallelization and run the scan sequentially, one token at a time. That's why you get transformer-level accuracy with linear scaling and near-constant memory usage per step. So why does this matter for AI research right now? Because it directly addresses the two biggest bottlenecks in scaling: compute cost and context window limits. You can train longer sequences, fine-tune on high-resolution modalities, and deploy models with dramatically lower latency. The trade-offs are real, though. State space models still struggle with certain types of compositional reasoning and explicit memory retrieval where attention's global view shines. They also require careful initialization and discretization tuning to avoid numerical instability in the state evolution. But the research trajectory is clear. Hybrid architectures that combine attention for local structure with selective SSMs for long-range flow are already showing promise. And as hardware-aware discretization methods improve, the gap is closing fast. If you want to dive into the actual math, the original papers walk through the continuous time formulation, the zero-order hold discretization, and the parallel associative scan implementation in detail. The next wave of research is already exploring multi-scale state spaces, adaptive discretization step sizes, and joint training with diffusion or autoregressive heads. The foundation is shifting, and understanding how these models actually process information is going to be essential for anyone building or researching next-generation AI. Let me know which architectures you're tracking, and I'll break down the next breakthrough paper in the series.